Hello and welcome to another video. This one is going to be about notions of divisibility, which you can find at the beginning of chapter 4, specifically section 4.1. Maybe we'll get into a little bit from section 4.2 also today. And so I just want to go over some of these concepts and some of the sorts of questions that we might end up asking you to think about. One good thing about this, so you'll see in these concepts that there is some new notation, as always with math concepts. But then these new concepts with their new notation will give us new types of questions to ask and proofs. So for example, we'll be able to use this new notation and these new concepts to say, okay, now prove this sort of thing, say by induction. But okay, what is it that we want to think about here? That is to say, what is divisibility all about? And so we start with this definition of integers. So here's our definition. Given two integers, let's say one is a and one is b, so they're both whole numbers. They could be positive or negative. And let's say with the number a not equal to 0. So we'll make that exception. Then we say, so then the phrase a divides b, that's what we're defining, means b equals some other integer, I'll say c, times a, for some other integer c. And the important notation here is that in this case we would write a and it's just a line b. This is literally pronounced as a divides b. Okay, so hopefully this definition makes sense, but let's just rehearse a few examples. So here's an example, I'll call it example 1. You should be familiar with the statement that 2 divides 6. Now in our new way of notating this, we could say the integer 2 divides 6. But let's see what this means. According to our definition, this should mean that the number 6 equals some other whole integer c times 2. And this is true since we can use c equals 3. So this notion of dividing, right, we've defined it in terms of really being a multiple. Maybe another way to say what we're saying here, so another version of this definition, is to say a divides b means b is a multiple of a. Okay, so what we probably want to see here is maybe a non-example. So here's a non-example. And hopefully this example makes a lot of sense. I could say 5 does not divide 8. Right, so notice my does not divide, I just wrote the divide symbol and put a slash through it. And this is pronounced 5 does not divide 8. Now we all probably know this to be true, but let's just spell out what this means in terms of our technical ability to write careful logical statements. So what this means is the number 8 can never be written as some integer times 5, where c is an integer. Okay, this isn't quite precise enough, although it's clearly communicating what we mean. What we're really saying here is the following. For every possible choice of integer, say c, 8 does not equal c times 5. That's really what we're saying. And if you go back up to the definition of divides, I really could have said this part here where I talk about b equaling c times a for some c. I could have used the existential quantifier here. There exists an integer c such that b equals c times a. So when you sort of clearly invoke that existential quantifier, to have a non-example, you're negating the definition of divides. So of course, we expect to see this negated existential, that is the universal. Okay. So here's a theorem that we can prove. Theorem. And it's really not saying anything too surprising. We just want to practice saying it with our new words. So the hypothesis for this theorem is going to say, suppose we have, or let a, b, and c be 3 integers where a does not equal 0. Okay, then the first, we're actually going to have 3 results here. 3 theorems, really, that I'm just collecting into one. And the first one, excuse me, oops, I lost my page, says, if a divides b and a divides c, then a divides b plus c. Okay, another one says, the second one says, if a divides b, then, so notice this one has fewer hypotheses, comma, then a divides b times c. And this is true for any other integer c, right? And then the third statement in this theorem might sound something like this. If a divides b, and if b divides c. So this one's, right, so if a divides b and b divides c, then a divides c. Okay, so let's maybe pick some of these to see how we might prove, how we might prove. And what I'll do is sort of sketch a proof. This is basically a full-blown proof, but because these are notes, I don't want to necessarily write every single word. So this is sort of a proof sketch. But for the first one, I'm going to say, suppose A divides B and A divides C. Well, like in lots of our proofs that we've practiced writing so far, we really only have one place to go after this. We have to tell our readers what this means. So what did I just do? I said, well, suppose A divides B, so this means B is some multiple of A. And notice I'm going to use a different letter. I'm going to say it's B equals M times A. And it also means C is a multiple of A, so maybe C equals some N times A, where M and N are integers. Right? All I did there was carefully show that, carefully show. All I did was carefully write down what it means to say A divides B and A divides C. Now I want to show that A divides this new number, B plus C. Well, notice we can now write that B plus C has to equal M times A plus N times A. And by accepted and allowed rules of arithmetic, I can rewrite this by factoring out an A. And now look what I have. I have B plus C equals a gigantic number times A. Right? I have B plus C equals some other integer times A. So this tells us, this implies that B, I'll say it like this, that A divides B plus C, right? Since what we're really noticing here is this term, M plus N, is itself some integer. So that would be a nice little proof for the first theorem. Maybe I'll assign part 2 for reading or a little homework write-up. So let's try part 3. And I'm going to need to add more pages. So give me a second here. This is super fun. Let's try this really quick. Sorry for the flow in talking, the interruption to the flow. All right, let's just insert a whole bunch of pages. Okay, probably won't take that many. Okay. All right, so back to where we were. All right. So now this third statement says, okay, if A divides B and if B divides C, then A also divides C. Let's just see a quick version of a proof of this. Again, we're going to suppose A divides B and B divides C. And now what I want to do is sort of write what this means. This means, so in green, this means B equals some number M times A. And this means C equals some number, maybe I'll call it Q times B. Right? And what do I know? M and Q are integers. So what are we trying to conclude here in this little result? We want to show that A divides C. That is, we want to show that c equals some integer, I'll give it a name in a second, times a. Maybe I'll call this, I don't know, d. And what do I have? Well, written in green is all I have to use. That b is an integer times a, and that c is an integer times b. So let's write out some of this. We'll have c equals an integer times b, but b itself equals an integer times a. And so now if I just regroup this, right, I can say, oh, that's q times m times a, right? And since qm is itself an integer, this is an integer. This could be what we call d, right? So the fact that a divides b and then b divides c does indeed show us that a divides c. And so if I wrote this up with the right amount of words and rearranged my writing, I could put a little proof square to end this. But in case these proofs felt sort of unnecessarily abstract, let's just think about some examples for this. Are we on example 2 or example 3? Sorry, for example 2. Okay. So example 2, for example, let's pick some numbers that we know work out. Let's say, we'll say, okay, 3 divides 6, so that's my a divides b, and 6 divides 24. In fact, let me write that with an and. So hopefully we're all familiar with these two facts, and it's not too hard to conclude, well, yeah, this does tell me that 3 divides 24. And that's all this third property was saying, right? It was saying, well, if you can write 6 as a number times 3, and you can write 24 as a number times 6, then you can combine these two and learn that 24 equals 4 times 2 times 3. So this would be 4 times 2, all times 3. And this shows that 3 divides 24. That's really all our proof for the third one did. So it's easy for these proofs to feel like they're a little more abstract or confusing than they actually are. But that's okay. If you try some actual explicit examples, these statements really aren't too bad. Okay, so let me introduce you to a term that I don't believe is in our textbook in this section, although it could be. All right, and so I'll say definition. And what I'm defining is a linear combination. It's just a good word to know. It pops up in a lot of other classes as well. Some of you may have heard this in your linear algebra class, and most notably, it's going to be a very similar definition to the one you may have seen in that class, but it's slightly different. So what I'm really talking about here is a linear combination of integers. And in linear algebra, you may have heard of this word being like a linear combination of vectors. So a linear combination of two integers, a and b. So we're starting with two integers, and we're going to form what's called a linear combination of them, is an expression, and this expression is always an integer of the form, and here's what it looks like. Something times a plus something times b, where the two somethings are also integers. So let me try an example again, like I mentioned above. Examples are really helpful for sorting out what the heck this is trying to say. So here's one example. Let's say I claim that 4 is a linear combination of the integers 2 and 3. And here's how. So I'll say since 4 equals, let's try, we could do it this way. 2 times 2, sorry, let me do it this way. Negative, well, I'm trying to think of a good linear combination here. Well, I guess I could do what I was going to do. 2 times 2 plus 0 times 3. That one works. All right, let's try another example of this word linear combination. I don't know. 7 is a linear combination of, I'll say 2 and 3 again, since 7 equals 2 times 2 plus 1 times 3. Okay, so that's just a word. When you have two integers and you form this combination of them using other integer multiples and add up these multiples, we call the whole thing a linear combination. And so we have a corollary that's kind of easy to phrase in terms of this. A corollary to those previous 3 theorem results says the following. If A divides B and A divides C, then A divides all linear combinations of B and C. If you want to say that in mathy symbols, you would say A divides M times B plus, I don't know, N times C for all M and N in the integers. Right, again, I'm going to kind of write a proof sketch, so I really should put this word proof in like quotes because I'm not writing a tremendous amount of words here. Just want to give you an idea for how you would put this together officially. But if you think about it, you're trying to show that A divides a multiple of B plus a multiple of C. And instead what you can show pretty easily that A divides a multiple of B. That happens from part 3 of our little theorem above. And A divides a multiple of C. That also happens from part 3 of the theorem above. Just realized I wrote that wrong. So, okay, but using statement 1 from the theorem above, we then get that since A divides a multiple of B and A divides a multiple of C, A has to divide the sum of these two integers. And so it divides this arbitrary linear combination. right? If you want to think of, again, a concrete example really helps show why this is true. So a concrete example might be, let's say I'm going to pick, A is going to be some number that's easy to work with, maybe 5. So 5 divides 10, and 5 divides 35. Again, I should put and. Then what we're saying is 5 divides any multiple times 10 plus any multiple times 35. And what you're used to thinking about from dealing with these sorts of expressions in your previous math courses for like a decade now is, 5 divides this because it clearly divides 10, and 5 divides this because it clearly divides 35. And so it divides this entire linear combination. All right, so this really isn't saying anything new. It's saying a bunch of old stuff in just a new way. All right. Okay, so I think I am looking at some notes for a second. Give me a second. Okay. So I think what I'm going to do right now is just looking over my written notes to see how I wanted to organize this. So for right now, I'm going to put on pause for a separate video. It'll be shorter. We're going to do a statement of what's called the division algorithm. And one of the things that I want to point out about this is it's called an algorithm, but it is by no means an actual algorithm the way we use that word. It is not a list of instructions that you can use to repeat. So I'm going to put algorithm in quotes, even though this is what it's always been called. It's actually a theorem, so it's actually stated as a theorem. And proving the theorem, if you wanted to go through a careful proof of it, can lead you to an algorithm. So as you start to figure out why this theorem is true, depending on how you set up the proof, you might be able to use that proof or use your understanding of the result to produce an algorithm. And so that's the first thing that I want to talk about, or I want to mention. And then in a follow-up short video, because I'm going to try and keep these a little shorter, I also want to talk about congruence relations. And really what this is really called modular arithmetic. So I'll post either a video about both of these topics or 2 other separate videos to keep them short. And just to add to this a little bit, what I want to mention here is, without going into too much detail, just the idea of congruence relations and modular arithmetic. So the way this works, just as sort of an outline, we need the division algorithm or some statement like it to tell us that any 2 integers can be divided, except you might have a remainder. So this is what the division algorithm says, but it actually is a relatively nuanced statement or theorem when you write it out carefully. But this is what it's telling us. If you give me an integer a and an integer b, just as long as a isn't 0, I can always try to divide b by a. Right? And what happens is you might get some nice number, but then you get some weird thing we call a remainder. And I'm going to, so this r is a remainder. So if I multiply this equation all through by a, what I really get is b equals a times an integer q plus a remainder r. Q is called the quotient and r is called the remainder. Okay, but we need a theorem or a statement like the division algorithm to tell us this always happens. And you probably already know that this always happens, right? So just as a, again, as a concrete example, you might say, well, 10 divided by 3, that's going to be like this repeating decimal. What I could instead say is 10 is equal to 3 times 3 plus 1. So in this case, we have that this was B, this was A, and then these other parts, this was Q, and then the sort of star of the show turns out to be this magic number 1, the remainder. Right, and if you wanted to write this using rational numbers, right, you could write this equation saying 10 divided by 3, it's 3 plus 1 over 3, plus 1/3. Okay, so here's the point though. Once we get something like the division algorithm stated, then the story picks up with what we call modular arithmetic. And so here's where we're going to pick up in the next video. We'll do some more careful examples, maybe a more careful statement of the division algorithm, just so we have it on record. And then we'll jump into modular arithmetic, and here's what it says. You're going to give me your favorite, I don't know, your favorite whole number or integer n, right? I'll say m. And here's what we're going to say. So you're going to give me, given a fixed integer m, right? Here's what you're going to talk about. You're going to say integer a is congruent mod m, that's the real phrase, to integer b means a couple different things. It means, one, m divides their difference, and it also means, so I'll just say is equivalent to, it also means that a and b have the same remainder when divided by m. So these two things here, what I've labeled 1 and 2, these actually mean the same thing. But we need the division algorithm to talk about what a remainder is. So this is what the focus is going to be on is what we call modular arithmetic, and the idea of what it's capturing is actually pretty intuitive. So, for example, we could say, I'll try to pick some examples. I could say, let's say example, let me put a little 1 there. I could say 3 is congruent to 5 mod 2. What I'm really saying is the number 3 is the same as the number 5, as long as you ignore remainders when you divide by 2. And the truth is, if you think about this, this is really saying 2 divides their difference. I could do 5 minus 3. That's true. I could also think of this as saying, well, the remainder, right, when you do 3 divided by 2, you first have a remainder of 1. And then when you do 5 divided by 2, you get a remainder of 1. Those are the same. And if you really think about this, this isn't that weird of a thing to do. It's just a little weird to carefully write this down using math, using our careful way of talking. For example, clocks work this way. They tend to work mod 12. And I'm going to ignore AM and PM for a second. So if I just ignore AM and PM, then if it's 5 o'clock right now, in 12 hours, my clock's going to say 5 o'clock again. Right? So we're ignoring multiples of 12, right? Which means we're working modulo 12. Okay, that was kind of rushed. The main point of this attempt at being a shorter video was the concept of divide and the concept of linear combinations. Alright, I will post some other videos pretty soon. I will talk to you guys later, and I'll be updating some information for our class. Thanks.